swear to God, I do not think I can live with Amanda again. Yeah.
I totally understand. Oh, she's the worst.
Yeah. Oh my God. Yeah.
Bro, we have to together next year.
Exactly, bro. Hell yeah.
I should apply for wellness.
I don't know what I'm gonna do.
Or like civic
I don't know who wants to
engagement.
live with me. I don't know what I'm gonna do.
Grad Center C?
I'm all alone.
Are you guys talking about housing?
Yes.
What if I told you that we actually had a mathematical algorithm that could help you with this problem?
Really?
Wow.
To do this, we will create a dual problem connecting roommate pairings to stable matchings. In 1921, David Gale and Lloyd Shapley proved that a stable matching is always possible for two groups of equal size. In this algorithm, a matching is considered stable if after completing the rounds of the algorithm, there is no pair A and B such that both participants prefer each other over their current matched partner. A matching is unstable if such a pair occurs.
Wait, but we don't have two groups of equal size. How does this work?
In 1985, Robert Irving constructed an algorithm to answer this question. The Irving algorithm takes one group with an even number of participants and has each member rank their preferences for all the other members. Then, using a two-phase approach, it determines if a stable matching exists, and if so, it gives the stable matching. Unlike the Gale-Shapley algorithm, this algorithm does not need two groups of equal size. The first phase of the Irving algorithm is quite similar to the Gale-Shapley algorithm. To begin, each student will rank their preferences from best to worst of who they would like to room with. Students will then begin proposing to their first choice. When student X receives a proposal from student Y, they have two possible choices for response. X can either reject Y's proposal if X already holds a better proposal, or X can hold Y's proposal for consideration while X waits to receive potential proposals from all other members. At the same time, as Y is proposing, X is also proposing to their preferences, starting from the first choice. They will then continue to propose to their second choice if the first choice rejects, and pause their proposals when a promise for consideration is given. At the end of phase 1, there are two possible outcomes. Everyone is holding a proposal for consideration, or one person is rejected by everyone. Let's see how we can use this to solve our friends Amanda, Belle, Carl, David, Eloise, and Fernando's housing problem. I've listed their preferences below.
So the first thing that's going to happen is each person is going to propose to their top choice until all 6 people have a proposal that they are holding for consideration. So A is going to propose to E, B is going to propose to A, C is going to propose to B, and D is going to propose to B, which means B has 2 proposals from C and from D. And because D is higher on B's list than C is, we will remove B from C's list and C from B's list, which means C will propose to their next top choice, which is F. And then E is going to propose to C, and F is going to propose to A. But now A has 2 proposals from B and from F. And because A prefers F over B, we will remove A from B's list and B from A's list, and B will propose to their next top choice, which is D, and now everyone has a proposal held for consideration. Now that everyone's holding a proposal for consideration, we can move to phase 2 of the algorithm where we reduce the lists according to our corollary so that if Y is holding a proposal for consideration from X, Y will delete every person lower on their list than X from their list, and those people will also remove Y from their lists.
Let's see this in relation to our example.
So A is going to propose to E, its top choice, and then E is going to remove every person lower than A on its list because at the worst case scenario, it has a proposal from A, so it would not accept anything lower. And so then we're going to remove E also from the list of F, B, and D, which E has removed from its list. And then B is going to propose to D, and because B is D's top choice, everything else gets removed from its list, so A, F, and C. And so we will then remove D from their lists as well. And next, we move on to C, who proposes to F. And so F is going to remove B from its list, which is lower than C. And F is going to get removed from B's list as well. And then E is going to propose to C, and C is then going to remove A from its list, and D is already removed, so C gets removed from A's list. And then F is going to propose to A, and so A is then has F added to the list, but nothing is left to remove. So these are the reduced lists. A has E and F, B has D, C has F and E, D has B, E has C and A, and then F has A and C.
Now we begin to see how the Irving algorithm is different than the Gale-Shapley algorithm, as we can have two potential choices for one person. To then find a stable matching, we proceed to use something called an all-or-nothing cycle.
So Lemma 3.2 tells us that if A1 through AR is an all-or-nothing cycle where we denote B1 to be the first person in A1's reduced list, then one of two things is true. Either in a stable matching in these reduced lists, either AI and BI are the same for all values of I or for no value of I, or if there is a stable matching in which AI and BI are partners, then there is another in which they are not. So we can see this in the list of preferences where A, C, E, and F have multiple options. Each person has two different choices in their preference list, versus B and D, who only have each other. So that B and D are the same for all values of I, whereas A, C, E, and F have a stable matching in which they are paired with one of their options and one in which they're paired with the other option. So we have two potential stable matchings for this problem: A with E, B with D, and C with F, or A with F, B with D, and C with E. And from Corollary 3.3, we know that if the original problem allows for a stable matching, then the stable matching is contained in the completely reduced set of preference lists as shown in this example.
But how do we figure out which stable matching is most ideal? We can do this by eliminating our cycle. First, we will find the first person with two options left. Let them be labeled A1. Here A1 equals A. Then let B1 be the second option of A1's list. Here B1 equals F. Now let AI plus 1 be the last member of BI's current list. So for B1, we have A2 equals C. We will continue labeling BI as the second option in AI's list and AI plus 1 as the last option in BI's list until we find some AI equals AI plus J or BI equals BI plus J. This is considered a cycle. Here we notice a cycle as we see that A1 equals A and A3 equals A. Our last step is to eliminate this cycle. We do this by having BI reject AI plus 1. In this case, F will reject C and E rejects A. We will now end up with a stable matching, so our algorithm is complete. In this example, our roommates would be Amanda and Fernando, Belle and David, and Carl and Eloise. By eliminating these cycles, what we have done is we have reduced our preference list so that each list contains just one person. This will give us a stable matching. But there's another instance that can occur. If one or more among a reduced set of preference lists is empty, then the original problem admits no stable matching. Let's see an example of this.
Wait, this isn't the preference I listed.
Let's try this again using new preferences.
In this scenario, we are now going to start from the beginning and go through the algorithm so that everyone is holding a proposal for consideration. So A proposes to B, B proposes to C, C to D, D to E, E to A, F to A, but A is going to reject F, and so F is going to move throughout its list to each following person, and everyone is going to reject F because F is last on everyone's list, which means all of F's proposals are rejected and F has no proposal to hold for consideration, which means this algorithm does not produce a stable matching.
Unfortunately, this means that Fernando is left all alone. Let's go break the news to him.
But what about me? This isn't fair.
Well, math isn't always fair, so.
We didn't say it was a perfect system.